Welcome to Hess's Law, one of the most powerful tools in thermochemistry. Germain Hess, a Swiss-Russian chemist, discovered in 1840 that the total enthalpy change of a chemical reaction is the same regardless of the number of steps or the pathway taken. This means we can calculate the enthalpy change for reactions that are difficult or impossible to measure directly, like the formation of carbon monoxide or the lattice energy of ionic compounds. In this presentation, we will explore why enthalpy is a state function, learn how to construct enthalpy cycles, master the manipulation of thermochemical equations, calculate reaction enthalpies using standard enthalpies of formation, and apply Hess's law through quizzes and detailed step-by-step problems. By the end, you will be able to determine the enthalpy change for almost any reaction using published data. Enthalpy H is a state function. Its value depends only on the current state of the system, not on how the system arrived there. Think of it like elevation. The change in elevation between 2 points is the same, whether you climb a steep path or a gentle trail. Similarly, the enthalpy change between reactants and products is the same, regardless of the reaction pathway. This is the fundamental principle behind Hess's law. State functions include enthalpy H, internal energy U, pressure P, volume V, and temperature T. In contrast, heat Q and work W are path-dependent. They describe how a change occurs, not just the initial and final states. Because delta H is the difference between the enthalpies of two well-defined states, we can add, subtract, and combine thermochemical equations, just like algebraic expressions. The formal statement of Hess's law reads, "The enthalpy change accompanying a chemical reaction is independent of the route by which the reaction occurs, provided the initial and final conditions are the same." This allows us to calculate delta H for a reaction by adding the enthalpy changes of a series of intermediate reactions whose sum equals the desired overall reaction. For example, if we cannot directly measure the enthalpy of formation of carbon monoxide from carbon and oxygen, we can measure the combustion of carbon to CO2 and the combustion of CO to CO2, then subtract to find the desired value. Remember these 3 rules. If you reverse a reaction, you flip the sign of delta H. If you multiply a reaction by a coefficient, you multiply delta H by the same factor. And if you add reactions, you add their delta H values. An enthalpy cycle is a visual representation of Hess's law. It shows how multiple pathways connect the same initial and final states through intermediate compounds. Each arrow represents a thermochemical equation with its delta H value. The power of the cycle is that the sum of delta H around any complete loop is 0, because you return to the starting state. To construct an enthalpy cycle, identify your target reaction, then find known reactions that connect the same species. Arrange them in a cycle diagram. Apply Hess's law by summing the delta H values around the cycle, making sure to follow the arrow directions. The most famous enthalpy cycle is the Born-Haber cycle, used to calculate lattice energies of ionic compounds. But simpler cycles apply to many organic and inorganic reactions. The key insight is that any reaction pathway, no matter how indirect, gives the same delta H as the direct path. Working with thermochemical equations requires 3 key operations. First, reversing an equation. When you reverse a chemical equation, the sign of delta H also reverses. If the forward reaction releases 100 kilojoules, the reverse reaction absorbs 100 kilojoules. Second, multiplying by coefficients. If you multiply all coefficients in a balanced equation by a factor n, you multiply delta H by the same factor n. Third, adding equations. When you add 2 or more equations to obtain a new equation, you add their corresponding delta H values. This is the core of Hess's law calculations. Always ensure that species not in the target equation cancel out. These are called intermediates. In the classic example, the formation of CO from carbon and O2 is found by subtracting the combustion of CO from the combustion of carbon. The intermediate CO2 cancels out, leaving the desired target equation. The standard enthalpy of formation, delta H F naught, is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states under standard conditions of 1 bar pressure and 298 Kelvin. Standard state means the most stable form of an element at 1 bar and the specified temperature. For example, the standard state of oxygen is O2 gas, of carbon is graphite, and of hydrogen is H2 gas. By definition, the delta HF naught of any element in its standard state is 0. These values are tabulated for thousands of compounds and are the most practical tool for applying Hess's law. To calculate the delta H naught for any reaction, use the formula. Delta H naught of reaction equals the sum of delta H F naught of products minus the sum of delta H F naught of reactants. This equation works because formation reactions can be added algebraically to construct any reaction. Hess's law has enormous practical value in chemistry. It allows us to determine enthalpies that cannot be measured directly in a calorimeter. The enthalpy of formation of CO cannot be measured directly because burning carbon always produces a mixture of CO and CO2. Using Hess's law with the combustion enthalpies of carbon and CO gives the answer. Lattice energy, the energy released when gaseous ions form an ionic solid, cannot be measured directly, but the Born-Haber cycle calculates it using ionization energies, electron affinities, sublimation energies, and bond dissociation energies. Reaction enthalpies for complex organic reactions, biochemical pathways, and industrial processes are routinely calculated from tabulated delta HF naught data. This principle is essential in drug design, materials science, and environmental chemistry. Test your knowledge with this question. Which statement best describes Hess's law of constant heat summation? Option A. The enthalpy change depends on the reaction pathway. Option B. The enthalpy change is independent of the pathway taken. Option C. Only exothermic reactions obey Hess's law. Option D. Hess's law applies only to combustion reactions. The correct answer is B. Hess's law states that the total enthalpy change for a chemical reaction is the same, regardless of the number of steps or the pathway taken, because enthalpy is a state function. It applies to all chemical reactions, both exothermic and endothermic. Quiz question 2. Why is enthalpy considered a state function? Option A. It depends only on the initial and final states. Option B. It depends on the reaction mechanism. Option C. It can only be measured at equilibrium. Option D. It varies with the catalyst used. The correct answer is A. A state function depends only on the current state of the system, not on how that state was reached. Enthalpy H is a state function, so delta H depends only on H products minus H reactants, not on the pathway. Quiz question 3. What happens to delta H when a thermochemical equation is reversed? Option A. Delta H becomes 0. Option B. Delta H is multiplied by 2. Option C. The sign of delta H is reversed. Option D. Delta H remains unchanged. The correct answer is C. When a chemical equation is reversed, the sign of delta H is also reversed. If the forward reaction releases 100 kilojoules, the reverse reaction must absorb 100 kilojoules to return to the original state. This follows from the first law of thermodynamics. Quiz question 4. What is the standard enthalpy of formation of O2 gas? Option A, 0 kilojoules per mole. Option B, 0 kilojoules per mole at 25 degrees Celsius only. Option C, negative 100 kilojoules per mole. Option D, it varies depending on the allotrope. The correct answer is A. By definition, the standard enthalpy of formation of any element in its standard state is 0. O2 gas is the standard state of oxygen at 1 bar and 298 Kelvin, so delta H F naught of O2 gas equals 0 kilojoules per mole. Final quiz question. Given reaction A to B with delta H equals plus 50 kilojoules and reaction B to C with delta H equals minus 30 kilojoules. What is delta H for A to C? Option A, minus 80 kilojoules. Option B, plus 80 kilojoules. Option C, minus 20 kilojoules. Option D, plus 20 kilojoules. The correct answer is D. Hess's law, delta H for A to C equals delta H for A to B plus delta H for B to C. Delta H equals plus 50 plus minus 30 equals plus 20 kilojoules. The reaction is endothermic overall. Problem 1. Calculating the enthalpy of formation of carbon monoxide using Hess's law. We are given reaction 1. Carbon solid plus O2 gas produces CO2 gas. Delta H equals negative 393.5 kilojoules. Reaction 2. CO gas plus half O2 gas produces CO2 gas. Delta H equals negative 283.0 kilojoules. Our target is carbon solid plus half O2 gas produces CO gas. Step 1. Keep equation 1 as given. Step 2. Reverse equation 2 to get CO as product. CO2 produces CO plus half O2, delta H equals plus 283.0 kilojoules. Step 3. Add the two equations. Carbon plus O2 plus CO2 on the left, CO2 plus CO plus half O2 on the right. Cancel CO2 and the extra half O2. Step 4. Add the enthalpies. Negative 393.5 plus 283.0 equals negative 110.5 kilojoules per mole. The formation of CO is exothermic. Problem 2. using standard enthalpies of formation to calculate the combustion enthalpy of propane. The reaction is C3H8 gas plus 5O2 gas produces 3CO2 gas plus 4H2O liquid. Given delta HF naught values, C3H8 is negative 103.8, CO2 is negative 393.5, H2O liquid is negative 285.8 kilojoules per mole. Step 1. Apply the formula delta H naught of reaction equals sum of delta H F naught of products minus sum of delta H F naught of reactants. Step 2. Calculate product sum. 3 times negative 393.5 equals negative 1,180.5. 4 times negative 285.8 equals negative 1,143.2. Total is negative 2,323.7 kilojoules. Step 3. Calculate reactant sum. 1 times negative 103.8 equals negative 103.8. 5 times 0 equals 0. Total is negative 103.8. Step 4. Subtract reactants from products. Negative 2,323.7 minus negative 103.8 equals negative 2,219.9 kilojoules per mole. This is exothermic combustion, which makes sense because propane is used as a fuel. Problem 3. Multiple manipulations with Hess's law to find the formation enthalpy of diborane. We need delta H for 2 boron solid plus 3H2 gas produces B2H6 gas. Given equation 1, 2 boron plus 1.5O2 produces B2O3 solid, delta H equals negative 1273 kilojoules. Equation 2. B2H6 plus 3O2 produces B2O3 plus 3H2O gas. Delta H equals negative 2035 kilojoules. Equation 3. H2 plus half O2 produces H2O gas. Delta H equals negative 242 kilojoules. Step 1. Keep equation 1 as is. Step 2. Reverse equation 2 to get B2H6 as product. Step 3. Reverse and multiply equation 3 by 3. Step 4. Add all three equations. Verify that O2 and H2O cancel properly. Step 5. Add the enthalpies. Negative 1273 plus 2035 minus 726 equals positive 36 kilojoules per mole. The formation of diborane is endothermic. Problem 4. Calculating lattice energy of sodium chloride using the Born-Haber cycle. Given data, delta HF naught of NaCl solid equals negative 411 kilojoules per mole. Sublimation energy of sodium is plus 108. First ionization energy of sodium is plus 496. Electron affinity of chlorine is negative 349. Bond dissociation energy of Cl2 is plus 242 per mole of Cl2. Step 1. Sublimation of sodium metal. Na solid to Na gas, plus 108. Step 2. Ionization of sodium gas. Na gas to Na plus ion plus electron, plus 496. Step 3. Dissociation of half a mole of Cl2 gas to Cl atoms, plus 121. Step 4. Electron affinity of chlorine. Cl gas plus electron gives Cl minus ion, negative 349. Step 5. Lattice formation is unknown. Na plus Cl minus forms NaCl solid. Step 6. Apply Hess's law. Negative 411 equals 108 plus 496 plus 121 minus 349 plus lattice energy. Solving gives lattice energy equals negative 787 kilojoules per mole. This large exothermic value explains why ionic compounds are stable. Problem 5. The water-gas shift reaction. Calculate delta H for carbon solid plus water vapor producing carbon monoxide and hydrogen gas. Given equation 1, carbon plus O2 produces CO2, delta H equals negative 393.5 kilojoules. Equation 2, 2H2 plus O2 produces 2H2O, delta H equals negative 483.6. Equation 3, 2CO plus O2 produces 2CO2, delta H equals negative 566.0. Step 1. Keep equation 1 as is. Step 2. Reverse and have equation 2 to make H2O a reactant. H2O produces H2 plus half O2, delta H equals plus 241.8. Step 3. Reverse and have equation 3 to make CO a product. CO2 produces CO plus half O2, delta H equals plus 283.0. Step 4. Add all three equations. Carbon plus H2O produces CO plus H2. Step 5. Add the enthalpies. Negative 393.